quantum physics, sleep, and the nature of reality. Three mysteries that reveal how strange and beautiful our universe truly is. I'm George, your quiet guide through the soft side of science. For years, I've told calm stories that help curious minds unwind, learn, and drift peacefully into sleep. Tonight, we'll explore the quantum world, a realm where particles blink in and out of existence. Time and matter behave like waves, and observation itself can change what's real. So take a slow breath, let your thoughts settle, and join me as we drift into the science of everything, softly and without hurry. If you enjoy these calm explorations and wish to hear more, a simple like or subscribe truly helps this sleepy little channel float along. And for those already subscribed, thank you. Your support means more than you might realize. Now, I'll try not to make tonight's topic so fascinating that it keeps you awake. But if it does, at least you'll come away with a deeper sense of why particles sometimes act like waves, and why reality itself seems to hesitate until someone looks. A small price to pay for a thoughtful night. So, let's begin. What is quantum physics, and why does it so often sound as though the universe is making things up as it goes? The world we know, the one we can see and touch, feels solid and predictable. Drop a teacup and it falls. Flip a coin and it lands. Close your eyes and the moon remains. Yet in the early 20th century, scientists began to look closer, much closer, and the deeper they peered into matter's inner workings, the stranger it became. Light, they discovered, could behave both like a wave and a particle. Particles, it turned out, could exist in several places at once until they were measured. And the act of observing something didn't merely reveal what was already there, it appeared to change it. This wasn't a fluke of bad data or fuzzy instruments. It was real, reproducible, and it shattered the tidy laws of classical physics that had ruled for centuries. Quantum physics wasn't simply a new branch of science. It was a new way of seeing reality, a world where certainty is replaced by probability, and cause does not always precede effect in the way we expect. In this video, we'll drift softly through that world. There's no need to grasp every equation or memorize every name. We'll move slowly, gently, one mystery at a time, from the earliest puzzles that nudged scientists off their classical perch to the questions that still keep physicists awake at night. So tuck yourself in, close your eyes if you like, and let's explore a world where even emptiness isn't truly empty, and where everything you thought you knew about reality is only probably true. At the turn of the 20th century, physics felt almost complete. The laws of motion were established. Thermodynamics was tidy. Light fit neatly within electromagnetic theory. It was a golden age of certainty. Some scientists even believed the great questions had already been answered. Only a few odd bits remained, small imperfections, like dust in the corners of a well-swept room. One of those dusty corners involved a simple idea. What happens when you heat an object? Warm a piece of metal or a lump of coal, and it glows, first red, then orange, then white, depending on temperature. This glow, called black body radiation, arises from how objects emit electromagnetic energy when heated. It was easy to observe and seemed like it should be easy to explain. Yet the mathematics refused to cooperate. Classical physics predicted something bizarre. As a black body's temperature increased, it should emit more and more energy at shorter wavelengths, particularly in the ultraviolet range. The problem was that this prediction led to infinite energy at high frequencies. an impossible scenario nicknamed the ultraviolet catastrophe. No amount of adjusting could stop the equations from spiraling into nonsense. Reality simply didn't match the math. Something was missing. Enter Max Planck. In 1899, Planck, a careful German theoretical physicist, wasn't known for rebellion. He firmly believed in the classical worldview, but he was also pragmatic, and when confronted with the black-body problem, he did something quietly revolutionary to fix the mathematics. Planck proposed a strange idea. What if energy couldn't be emitted in arbitrary amounts? What if it came only in tiny, indivisible packets like coins that cannot be split? These packets would represent the smallest possible units of energy. He called them quanta. This was a dramatic shift from the smooth, continuous view of energy held by classical physics. Instead of flowing freely, energy would arrive in step-steiny jumps depending on the radiation's frequency. Planck even introduced a constant now called Planck's constant to describe the size of these energy packets. It was unimaginably small, yet mathematically elegant. When he inserted it into his equations, something remarkable happened. The infinite energy problem vanished. The equations worked, matching the real world. Planck had solved the ultraviolet catastrophe, and yet he didn't quite believe it. He described his fix as a mathematical trick, a clever patch, rather than a glimpse of nature's true workings. He assumed future scientists would find a better explanation that didn't require such peculiar assumptions. Quantization to him was temporary, not fundamental. What he couldn't have known was that his trick would become the cornerstone of an entirely new way of thinking. The idea that energy comes in discrete packets laid the foundation for quantum theory, a theory that would soon unravel much of what classical physics had taken for granted. It's easy to look back and see this as the moment everything changed, but at the time, it felt more like an odd side note than a revolution. Planck hadn't set out to rewrite reality. He simply wanted his equations to make sense. Yet in introducing quantization, he had lit the first spark in a slow-burning fire that would reshape our understanding of light, matter, and the nature of existence itself. This humble beginning, tucked into a quiet paper published in 19, carried no grand declarations, just a constant, a new way of thinking about energy, and a curious fix for a stubborn problem. From that point on, physics would never again feel truly complete. By the early 1900s, light seemed well understood. Thanks to James Clerk Maxwell's equations, scientists knew it behaved like a waving, elegant ripple through the electromagnetic field. It bent, bounced, diffracted, and interfered just as waves should. And after Max Planck's quiet introduction of energy quanta, most assumed things would soon settle into a new normal. But then came a riddle involving metal, light, and a surprising refusal to cooperate: the photoelectric effect. It worked like this. When you shine light onto a metal surface, electrons can be ejected from that metal. The idea made sense. Light carries energy, and energy can knock electrons free. No mystery there. According to classical wave theory, increasing the brightness of the light should increase the energy transferred to the electrons. A brighter wave should shake electrons loose more effectively. That was the reasonable expectation, but that's not what happened. Experiments revealed something strange. Shining brighter light didn't always eject electrons with more energy. What mattered most was the light's frequency. If the frequency was below a certain threshold, even the brightest beam produced no electrons at all. But once the light rose above that frequency, Even a faint beam could knock them loose with ease. The threshold was sharp, and it made no sense within classical physics. What had seemed a small inconsistency became a full-blown puzzle. Enter Albert Einstein. In 1905, his so-called miracle year, Einstein published a paper that changed everything. To explain the photoelectric effect, he proposed something bold. What if light wasn't purely a wave? What if, under certain circumstances, it behaved like a particle, a tiny packet of energy traveling in a straight line? Einstein suggested that light consisted of individual energy bundles, which he called quanta of light, later known as photons. Each photon carried a specific amount of energy determined by its frequency. If a photon had enough energy, it could knock an electron out of the metal. If it didn't, no amount of extra brightness would help. It was like trying to open a locked door with a handful of wrong keys. No matter how many you tried, none would fit. Einstein's idea built directly on Planck's earlier work, but went further. He wasn't treating energy packets as a mathematical convenience. He was claiming that light itself was made of them, a literal description of nature. It was a revolutionary thought, and not everyone liked it. Many physicists clung tightly to the wave model of light. After all, light clearly behaved like a wave. It diffracted, it interfered, it rippled. If light were made of particles, how could it also form those smooth wave patterns? Einstein didn't deny the wave nature of light. Instead, he suggested something far stranger. Light was both a wave and a particle. It could act like one or the other, depending on how you observed it. This dual nature wasn't an illusion. It was built into light itself. Imagine sunlight filtering through a window. It spreads and dances like a wave, bouncing off dust and glass. But if you zoomed in deeply enough, you'd find tiny photons, each carrying a discrete packet of energy, striking atoms one by one, changing the world in microscopic steps. This wave-particle duality is among the strangest ideas in all of physics, not because it's complicated, but because it challenges our basic categories of reality. In the classical world, something is either a wave or a particle, not both. Yet the quantum world doesn't ask our permission to make sense. Einstein's photon theory not only matched experimental results, it did so elegantly. The energy of each photon depended on its frequency, exactly as Planck had proposed. It explained perfectly why low-frequency light, no matter how intense, could not eject electrons. The photons simply lacked the necessary energy. The impact was enormous. In 1921, Einstein received the Nobel Prize, not for relativity as many assume, but for his explanation of the photoelectric effect. That's how fundamental the discovery was. Still, Einstein himself remained uneasy. He resisted the deeper probabilistic implications that came later. God does not play dice with the universe, he famously said. But dice or not, the rules were changing, and at their heart lay a strange truth. Light refused to fit into any tidy box. It came in quanta. It danced as a wave. It collided like a particle. It shimmered between states, revealing just enough to keep us wondering. What began as a simple experiment with metal and light ended up shaking the foundations of physics. Because if light could behave both continuously and discretely, what else might the universe be hiding in its quiet corners? Imagine setting up a simple table experiment. You place a flashlight at one end, cut to tiny slits in a piece of cardboard, and shine the light through them onto a screen behind. Hardly thrilling, and yet, this humble setup hides one of the most astonishing experiments ever performed. The double-slit experiment has become legendary, not for its complexity, but for its implications. Some physicists even joke that it's the most dramatic experiment of all time, starring a flashlight, 2 holes, and a piece of cardboard. Let's start with expectations. In the world of classical physics, waves and particles behave differently. Waves spread out and interfere with themselves. Picture ocean waves passing through 2 gaps in a barrier. They overlap on the far side, creating a pattern of peaks and troughs. That's interference. Now picture particles, tiny rubber balls fired at a wall with 2 slits. Some pass through the left slit, some the right. They don't interfere. On the screen behind, you'd expect to see 2 clusters of impacts, mirroring the 2 openings. So what happens when you do this with light? When scientists first passed light through 2 slits, it behaved like a wave, forming an interference pattern, alternating bright and dark bands caused by overlapping wave peaks and troughs. Perfectly wave-like. Then they turned down the light, using extremely sensitive detectors to release just 1 photon at a time. Each photon traveled toward the slits alone. You'd expect it to go through one slit or the other, right? Yet, when enough single photons accumulated on the screen, they formed the same interference pattern. Somehow, each photon behaved as though it had gone through both slits simultaneously and interfered with itself. How could a single photon interfere with itself? Was it splitting, ghost-like, through both paths at once? The results were undeniable. The interference pattern persisted even when particles were sent one at a time. Physicists then tried a natural next step to watch which slit each photon passed through. They added detectors at the openings, expecting to settle the question. Did the photon choose left or right? But the moment they observed the photons, the interference vanished. The pattern collapsed into 2 neat bands, just as if the photons were classical particles again. Simply observing forced each photon to decide. Turn off the detectors, and the interference returned. Turn them on again, and it disappeared. It was as if the very act of measurement compelled reality to choose. The experimenters weren't disturbing the photons. The equipment was passive. It was the knowledge itself that seemed to matter. Reality, it seemed, cared whether it was being watched. This wasn't a one-off quirk. The double-slit experiment has been repeated countless times with photons, electrons, even large molecules made of hundreds of atoms, and always with the same results. Left unobserved, the particles behave like waves, forming interference patterns. Observed, they act like solid particles. The implications were staggering. The experiment sits at the heart of quantum physics because it refuses to fit any comfortable logic. It suggests that on the smaller scales, particles do not follow strict paths. They exist as a spread of possibilities, a shimmering cloud of potential outcomes. Only when we measure them do those possibilities collapse into something definite. Some scientists picture this as a wave that splits and others see it as a cloud of probability. And still others, those in the many worlds camp, imagine each possible path branching into its own universe. Whatever the interpretation, the fact remains. Until observed, a quantum object does not commit to a single reality. What began as a simple test of light became a profound lesson about existence itself. The universe, it turns out, is not a clockwork mechanism, but a living tapestry woven from possibilities, and it seems to respond in curious ways to our gaze. With 2 slits, a beam of light, and a screen, we discovered that the cosmos winks at us when we're not looking and stands still when we are. In the strange, whispering world of quantum physics, if there's one piece of mathematics that hums quietly through everything, it's Schrödinger's equation. Don't worry, this isn't going to be a math lecture. No one lies awake dreaming of partial differential equations. But this equation is different. It's not just symbols on a chalkboard. It is, in a way, the heartbeat of the quantum realm. Back in the 1920s, physicists were struggling to describe particles that refused to behave like ordinary particles. Electrons were showing wave-like patterns. Photons were behaving like probabilistic ghosts. Newton's laws no longer fit. The universe seemed to require a new kind of language. Enter Erwin Schrödinger. In 1926, he proposed an equation that described not only how particles move, but how their wave functions evolve through time. It was elegant, compact, and astonishingly powerful at its core. The equation tells a simple story, shows how a quantum system changes to understand it. We first need to grasp the idea of the wave function, usually written with the Greek letter psi. Think of it as a kind of mathematical whisper that contains everything knowable about a particle, where it might be, how likely it is to be there, and how it might move. The wave function doesn't give firm answers. It gives probabilities. In classical physics, a particle is a point following a clear path. In Schrödinger's world, it's a hazy ripple, a soft cloud of possibility. The equation shows how this cloud flows and evolves over time. And when we finally measure the particle, when we ask, "Where are you?" that wave collapses. The haze vanishes, and we get a single definite answer. "Here I am," says the universe. Just for that moment, this wave-based vision of reality was a complete break from the mechanical picture that had reigned since Newton. Instead of solid bodies tracing predictable orbits like planets, Schrödinger showed us fields of probability fluid, uncertain, and beautifully strange. Imagine you're blindfolded in a quiet room. Somewhere, a cat is padding softly. You can't see or hear it, but you toss tiny balls and listen to where they land. Over time, you build a picture of where the cat might be, areas of higher or lower likelihood. That mental map is like a wave function, not a snapshot of what is, but of what might be. Now imagine an equation that can tell you how that likelihood shifts with time. Perhaps the cat tends toward the warm corner or curls near a cushion. That's what Schrödinger's equation does, only for electrons instead of cats. The actual mathematics is smooth and continuous, allowing those waves of probability to ripple through space like patterns on water. It respects nature's symmetries, energy, momentum, time, but it has no love for certainty. It tells us what could happen, not what will happen. What makes it extraordinary is how well it works. Physicists have used Schrödinger's equation to explain the structure of atoms, the formation of molecules, the behavior of semiconductors, even the phenomenon of superconductivity. One of its great triumphs came with the hydrogen atom, the simplest of all. Before quantum mechanics, no one could explain why electrons stay in fixed orbits instead of spiraling into the nucleus. Schrödinger's equation revealed that electrons aren't little planets whizzing around. They form standing, wave-stable ripples of probability around the nucleus. These standing waves are the famous orbitals you've seen drawn in textbooks as misty clouds. They aren't just artistic illustrations. They describe the actual likelihood of finding an electron in a given place. So, electrons don't orbit, they reside. They dwell in zones of probability, held in graceful suspension by the mathematics of Schrödinger's equation. It's an astonishingly successful idea. The equation has predicted experiment after experiment with near-perfect accuracy. It remains one of science's most beautiful pieces of mathematics. Yet it's still abstract. You can't see or touch a wave function. It exists in the quiet realm of possibility. And then there's the philosophical side. What is a wave function, really? Is it something physical and actual part of reality, or just a description of our knowledge? Different interpretations of quantum mechanics argue endlessly about this, but the equation itself doesn't take sides. It simply works, whispering its predictions with unfailing precision. Even Schrödinger had mixed feelings. He was proud of the equation, yet uneasy about what it implied that things don't have definite properties until they're measured. His famous cat thought experiment was meant as a protest, a way to highlight the absurdity of that idea. Still, what he created changed everything. In a universe obsessed with yes and no, Schrödinger offered maybe. His equation doesn't command, it suggests. It flows like a tide through the uncertainty beneath everything at the tiniest scales. Motion isn't always motion, and position isn't always position. Certainty becomes a luxury, but through one elegant equation, we can still navigate the haze in the classical world of apples, bicycles, and bowling balls. You can know both where something is and how fast it's moving. A radar gun can measure a car's speed while GPS tells you its location. No paradox there. But in the quantum world, those certainties break down in the 1920s. Werner Heisenberg introduced a principle so subtle and so central that it still makes physicists pause. It's called the uncertainty principle, and it tells us there are limits to what we can know. Specifically, the more precisely we know a particle's position, the less precisely we can know its momentum and vice versa. At first glance, it sounds absurd. If you see a train pulling into a station, you know where it is and how fast it's going. Why should that ever fail? But at the quantum scale, the universe doesn't allow that level of clarity. The uncertainty isn't a flaw in our instruments, it's built into reality itself. Imagine trying to observe an electron. To see it, you shine light on it. But light is made of photons, and photons carry energy. When one hits the electron, it changes its motion. It's like trying to find a soap bubble by throwing tennis balls at it to find it, but you'll also destroy it. Yet Heisenberg's insight went deeper than that. Even with a perfect, non-intrusive measurement, the uncertainty would remain. It isn't caused by disturbance, it's part of the quantum fabric at its heart. The principle comes from the wave nature of particles. A particle isn't a point, it's a wave spread through space. You can locate a wave crest roughly, but you can't define its momentum exactly at the same time. Make the wave shorter and sharper to fix its position, and its momentum becomes wildly uncertain. It's a cosmic trade-off that no one can escape. The product of these uncertainties, position and momentum, is always greater than or equal to a tiny constant. Planck's constant divided by 4 pi. It's a small number, so in everyday life we never notice it. But for electrons and atoms, it shapes everything. Try to confine a particle too tightly, and it rebels. The narrower you squeeze its position, the more chaotic its momentum becomes. Nature refuses to be pinned down. One way to picture it is like holding mist in your hands. The tighter you squeeze, the less you have. Loosen your grip, and it lingers. That's uncertainty, not chaos, but graceful ambiguity. It's not a flaw. It's what gives the universe texture. It prevents atoms from collapsing. If an electron could sit still inside a nucleus, its position would be known perfectly, forcing its momentum to be infinitely uncertain, impossible. So, uncertainty holds atoms together, making stability itself a quantum gift. This principle extends beyond position and momentum. It applies to energy and time, angular momentum and orientation, everywhere in the quantum realm. It's a universal truth written into existence. And while it sounds frustrating, it's also strangely comforting. It reminds us that knowledge has limits not because we fail to measure carefully enough, but because reality itself is softly blurred at the edges. It invites us to make peace with not knowing, to sit quietly within the gentle fog of possibility. In our everyday experience, things are usually one way or another. A coin lands heads or tails. A light switch is on or off. Your tea is hot or cold, though sometimes questionably lukewarm. But in the quantum world, this tidy division collapses completely. Objects at the smallest scales don't always choose a side. They can hover in a strange in-between, a blend of all possible outcomes. This is the realm of quantum, superposition. To picture it, imagine flipping a coin. In the classical world, once it leaves your hand, it spins through the air. Already determined as heads or tails, it's just hidden from you until it lands. In the quantum world, the coin isn't secretly one or the other. It's both. It exists in a superposed stator mixture of all possibilities until you look. When you finally observe it, the superposition collapses. The quantum coin chooses, and your measurement becomes real. Before you looked, it wasn't undecided. It truly was both. That's the heart of superposition, and it's deeply strange. The idea was first introduced to describe the behavior of electrons and photons. Instead of following clear paths, these particles exist as wave functions, mathematical patterns of probability. Each possible stator spin, up or down, a photon going left or right, coexists in that function. All the possibilities live side by side until a measurement selects one. You might imagine it as a foggy landscape of outcomes. The particle isn't walking one path, smeared across every route it could take. The moment you interact with it, that fog snaps into a single form, like lightning revealing one ridge in the mist. This leads to one of the most famous thought experiments in physics, Schrödinger's cat. Imagine a sealed box containing a cat, a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers and releases the poison, killing the cat. If the atom doesn't decay, the cat survives. Quantum mechanics tells us that until you observe the atom, it exists in a superposition of decayed and not decayed states, which means, absurdly, the cat is both dead and alive until you open the box. Schrödinger didn't mean this to be taken literally. He was pointing out how bizarre it is to apply quantum rules to everyday objects. Yet the image stuck because it captures the essence of quantum indeterminacy in one haunting metaphor. Before observation, a system contains every possible outcome, all coexisting until one becomes real. Superposition isn't a flaw of quantum theory, it's one of its most powerful features. In fact, modern technologies depend on it. Take quantum computing. A classical computer stores information in bits that are either 0 or 1. A quantum computer uses qubits instead, and a qubit can exist in a superposition of both 0 and 1 simultaneously. It's not switching between them. It's truly both at once. This means a single qubit holds more information than a classical bit. And when multiple qubits become entangled, they can represent an enormous number of combined states. That's why quantum computers can, in theory, perform certain calculations vastly faster than traditional ones. They don't just process one possibility, they explore many at once. It's not magic. It's mathematics playing by quantum rules. Problems like molecular simulations or optimization tasks that would take classical computers centuries could, someday, become tractable through superposition and entanglement. Superposition also has practical uses beyond computation. In quantum cryptography, it helps ensure that messages can't be intercepted without detection. In quantum sensing, it allows scientists to measure infinitesimally small changes in magnetic or gravitational fields. But there's a catch. Superposition is delicate. A quantum system can lose its coherence when disturbed by the slightest interaction, light, vibration, even a stray air molecule. The wave function collapses, and the fragile superposition disappears. This process, called dicoherence, is one of the biggest challenges in building stable quantum technologies. It's like trying to balance a feather on a pencil tip while someone breathes nearby. The more connected the system becomes to its environment, the faster its quantum behavior fades. That fragility makes superposition both mysterious and precious. It offers enormous potential but demands perfect stillness to survive, and beneath its technical uses lies a deeper philosophical question. If a particle can exist in multiple states at once, is that reality or just a reflection of what we know? Some interpretations of quantum mechanics suggest that the wave function represents our knowledge, a catalogue of possibilities. Others argue that it's physically real, that the particle truly is in several states until forced to choose. Either way, superposition teaches us something profound. It shows that opposites can coexist. A system can be this and that, here and there, yes and no, all at once. Reality, it seems, is not a single thread but a woven tapestry of possibilities, overlapping and unresolved until we observe them. It's strange and unsettling, but also beautiful, a reminder that the universe is not rigid but flexible, not mechanical but poetic. Imagine you have two gloves, one left-handed and one right-handed. You place each into a separate box and send one far away. You don't know which box holds which glove, but the moment you open one and see a left-handed glove, you instantly know the other must be right-handed. Nothing mysterious about that. The gloves were always one left and one right. Quantum entanglement, however, is nothing like that. Entangled particles aren't predetermined gloves. They're more like gloves that don't decide which hand they fit until after one box is opened. Whichever glove you check first somehow determines what the other will become. Instantly, no matter how far apart they are. It's not that the results are simply correlated. The properties themselves don't seem to exist until the moment of measurement. When you measure one, the other reacts instantly, as though connected by an invisible thread that stretches across space. This is quantum entanglement, one of the strangest, most baffling features of the quantum world. Here's how it works. When two particles interact in a certain way by being created together, colliding, or otherwise becoming linked, their quantum states become intertwined. Whatever happens to one affects the other, even when they're separated by vast distances. Imagine producing two photons, whose polarizations are uncertain until measured. One might turn out vertical, the other horizontal, but they don't decide beforehand. They remain in a shared superposition of all possible outcomes. Only when you measure one photon does its state become definite and at that very instant. the other photon state becomes definite too. If one is measured in Paris and the other in Tokyo, they respond simultaneously, as if the universe updated both at once. Einstein famously called this spooky action at a distance. He didn't like it. He believed that physical processes should be local, that nothing could influence something far away, faster than light could travel. Relativity depends on that idea. To Einstein, the suggestion that two distant particles could coordinate outcomes instantly was unacceptable. He was convinced that quantum mechanics must be incomplete, that there must be hidden variables behind the scenes, quietly determining everything in advance. In 1935, together with Boris Podolsky and Nathan Rosen, Einstein published a paper arguing this exact point. If quantum theory really allowed such instant connections, they reasoned, something crucial must be missing. But decades later, experiments began to show that the quantum view was right all along. In the 1960s, physicist John Bell devised a clever mathematical test Bell's theorem. It showed that if local hidden variables existed, certain statistical patterns would appear in entanglement experiments. If not, the results would follow quantum predictions. Again and again, experiments favored quantum mechanics. Entangled particles behaved in ways no local theory could explain. The results were random yet perfectly correlated, as though the particles shared a hidden script written outside space and time. Still, this instant link can't be used to send messages faster than light. Nature protects causality. When you measure your particle, the outcome is random. You can't control it or use it to transmit information. The connection is real but unexploitable. Like two people flipping coins on opposite sides of the galaxy and always getting complementary results without ever speaking. Even more astonishingly, distance doesn't weaken it. Experiments have entangled photons across rooms, continents, and even between Earth and orbiting satellites, and the correlations remain flawless. So what exactly is entanglement? Is it a kind of invisible tether, a shared identity, or a network of information woven between particles? The truth is, no one fully knows. Different interpretations of quantum mechanics tell different stories. Some say entanglement reflects knowledge, our description of the system, not the system itself. Others suggest it reveals a deep, non-local fabric of reality, where separateness is an illusion. Some even propose that space and time themselves emerge from webs of entanglement, that it's not something that happens within space, but something that creates space. Whatever the truth, entanglement isn't just theoretical, it's practical. It forms the basis of quantum teleportation, where the quantum state of one particle can be transferred to another at a distance. It underlies quantum key distribution, enabling unbreakable encryption. If anyone tries to eavesdrop, the entanglement collapses and the interference is instantly detectable. In quantum computing, entanglement allows qubits to act together in intricate patterns that can't be reduced to individual parts. It's what gives quantum computers their extraordinary potential for parallelism and power. What once unnerved Einstein now powers some of the most advanced experiments on Earth. Entanglement reminds us that the universe is not a collection of isolated pieces, but an interwoven whole. Even when things appear separate, at the deepest level they may still be connected. You don't wake up entangled with your neighbor, or find your morning coffee reflecting the state of someone else's spoon. Yet, at the tiniest scales, this silent partnership between particles hums quietly everywhere, all the time. And perhaps that's the most beautiful part of all that. even in a vast and silent cosmos, beneath the spaces between stars, there is still an echo of togetherness, instant, invisible, and unshakably real. There are few animals in science more famous than Schrödinger's cat. This curious creature has become the unofficial mascot of quantum physics. Thought experiment so peculiar that it's often mistaken for a joke. In a way, it was. Schrödinger never intended it to be taken literally. Yet, like all good metaphors, it touches something deep and uncomfortable at the heart of quantum theory. The story begins in the 1930s, when physicists were struggling to understand what quantum mechanics really meant. The math worked perfectly, the predictions were exact, but the interpretation was puzzling. What did it say about the world? Was the wave function a real, physical thing? Did particles truly exist in multiple states until they were measured? Or was the wave function just a mathematical tool for calculating outcomes? Erwin Schrödinger, already renowned for his beautiful equation, was skeptical of how far some physicists had pushed the idea of superposition, especially when it came to measurement. In his view, it made little sense to treat large, everyday objects as though they followed the same strange rules as electrons. So he posed a dark, playful question. What would happen if you scaled that weirdness up to something you could actually hold a living cat? Imagine a sealed box. Inside is a cat, a single radioactive atom, a Geiger counter, a vial of poison, and a trigger mechanism. If the atom decays a random event, according to quantum theory, the counter detects it. The trigger releases the poison, and the cat dies. If the atom doesn't decay, the cat lives. Here's the twist. Quantum mechanics says that until the atom is observed, it exists in a superposition of decayed and not decayed. That means the entire system, the detector, the poison, and yes, the cat is also in a superposition. The cat is both alive and dead at the same time. Schrödinger never built the box. He wasn't suggesting an experiment. He was making a point. He found it absurd to imagine that a catter, warm, purring, very real creature could exist in such a blurry state. His thought experiment was meant as a critique, not a proposal. And yet, the idea caught on. It distilled the weirdness of quantum mechanics into a single, unforgettable image. A cat that's both alive and dead until you look. It perfectly illustrates the problem of measurement, the gap between the smooth, evolving wave function and the definite outcomes we actually see. In quantum mechanics, observation plays a special role. Before you measure a system, it exists in a cloud of possibilities, each encoded in the wave function. The instant you interact with it by measuring, detecting, or even just obtaining information, the wave collapses. One possibility becomes real. The rest vanish. But what counts as a measurement? Is it the presence of a conscious observer, a mechanical detector, or simply any interaction with the environment? Different interpretations give different answers, and that uncertainty is exactly what makes Schrödinger's cat so haunting. It forces us to ask where, if anywhere, the boundary between quantum and classical really lies. The Copenhagen interpretation, favored by Niels Bohr and Werner Heisenberg, says that asking what happens before observation is meaningless. The cat isn't secretly alive or dead, it simply doesn't have a definite state until we open the box. Measurement doesn't reveal reality. It creates it. Other physicists preferred the many worlds interpretation, which avoids collapse entirely. In that view, when you open the box, the universe splits. In one branch, the cat lives. In another, it dies. Both outcomes are real, each unfolding in its own separate world. You just experience one of them. A third perspective decoherence theory argues that the cat isn't truly both alive and dead, just entangled with its environment in a way that makes its quantum behavior invisible. The superposition still exists in principle, but it's spread across so many degrees of freedom that we can't observe it. Each interpretation carries its own philosophical weight, but all agree on one thing. Quantum systems do not behave like miniature classical ones. They don't sit passively, waiting to be discovered. They evolve as clouds of probability, branching and merging in ways that defy common sense. So what does this mean for the cat? It means the box isn't just a container, it's the boundary between two worlds. Inside, quantum laws reign. Outside, we see definite outcomes. Somewhere in between lies the transition from possibility to reality. That's why Schrödinger's cat endures. It's not about life and death, it's about knowledge. It asks what it means to know something when knowing itself changes the outcome. It challenges us to question whether reality exists independently of observation, or whether, in some subtle way, we help shape it by looking. And perhaps the most unsettling question of all: if opening the box collapses the cat's wave function, what collapses ours? Where does the chain of observation end? Are we, too, part of the system, caught in our own quantum superpositions, until someone or something looks at us? Schrödinger's cat wasn't meant to be comforting. It was a mirror held up to the mystery of existence, a reminder that certainty is rare, clarity is conditional, and sometimes the universe waits for us to peek inside the box. In the everyday world, walls behave predictably. If you throw a tennis ball at one and it doesn't have enough energy to pass through, it bounces back. Simple, solid, and obedient to classical physics. But in the quantum world, predictability takes a curious turn. A particle can strike a wall, lack the energy to get through, and yet still appear on the other side without breaking, squeezing, or tunneling a hole. It simply shows up there, as if the barrier were not entirely real. This phenomenon is called quantum tunneling. And though it sounds impossible, it's measurable, repeatable, and absolutely fundamental to how the universe works. The explanation lies in the nature of wave functions. In quantum mechanics, a particle like an electron isn't a hard sphere, it's a wave of probability that fades gradually through space rather than stopping sharply. That means even in regions it shouldn't reach, the wave doesn't vanish entirely. It just weakens. Now imagine a particle approaching a barrier, region of space where the energy required to cross is greater than the energy it has. In classical physics, that's the end of the story. But the quantum wave doesn't stop at the wall. It stretches into it. The deeper it goes, the smaller the amplitude becomes, but not instantly to zero. And if the barrier is thin enough, that faint wave can emerge on the far side. If part of the wave survives the passage, there's a small but non-zero chance that the particle itself will appear there. The particle hasn't climbed over or smashed through, it's simply tunneled across the forbidden zone. It sounds like magic, but it's just math. Quantum tunneling isn't a rare curiosity, it's happening all the time. One of its most important roles is in radioactive decay. Some atomic nuclei are unstable and emit particles, like alpha particles made of 2 protons and 2 neutrons. According to classical physics, those particles don't have enough energy to escape the nucleus. Yet, they do. Inside the atom, their wave functions stretch toward the edges of the nuclear barrier. Occasionally, one tunnels through, escaping into the outside world. That's radioactive, decaying to bang, but a whisper through a wall. Without tunneling, many elements would remain forever locked in their nuclear prisons. The slow ticking of radioactive decay, the heat inside the Earth, the dating of ancient rocks owes its existence to this ghostly quantum passage. Tunneling also fuels the stars in the heart of the Sun. Hydrogen nuclei are packed together under crushing pressure and intense heat. Yet even there, they don't have quite enough energy to overcome their mutual electric repulsion and fuse. According to classical calculations, fusion should happen far less often than it does. And yet, the Sun shines. Quantum tunneling provides the answer. The proton's wave functions overlap. And though the chance of one tunneling through the repulsive barrier is tiny, the number of collisions is so immense that fusion proceeds steadily. The stars burn because particles can do the impossible. Here on Earth, tunneling plays a quiet role in technology. The scanning tunneling microscope, one of the most precise instruments ever built, uses it to map surfaces atom by atom. A sharp metal tip is brought extremely close to a surface, just a few nanometers away. At that distance, electrons can tunnel across the gap, creating a faint current. By measuring that current, scientists can reconstruct a detailed image of the surface without ever touching it. It's a kind of quantum sight, vision through proximity. Tunneling also appears in electronics. In some components, like tunnel diodes and quantum dots, it's not a nuisance but a feature. Yet, as transistors become smaller and smaller, tunneling becomes a challenge. At nanometer scales, electrons can slip through barriers that were once impenetrable, leaking current where none should flow. The walls in our circuitry, once solid, are beginning to blur. That presents both a problem and an opportunity. It makes classical devices harder to control, but it also opens doors for quantum technologies that harness tunneling rather than fight it at its heart. Tunneling reveals something profound about reality. We think of walls as absolute, of energy limits as firm, of space as divided into allowed and forbidden zones. But in the quantum world, boundaries are soft. Nothing is truly impassable. Everything is a matter of probability. A barrier doesn't say never, it says rarely, and given enough time, rarely becomes inevitably. Because of tunneling, particles are never entirely confined. They can drift, leak, appear, and vanish in ways that remind us the universe is not made of rigid edges, but of gentle gradients and shifting likelihoods. The tennis ball still bounces back from the wall, but the electron, the photon, or the alpha particle may glance at that same wall and quietly decide to pass through, and somehow nature lets them. One of the quiet revolutions of the 20th century was the realization that everything matter, energy, light, and even the vacuum can be described as fields. What we think of as particles are simply localized excitations, tiny ripples in these fields that spread throughout all of space. This framework is called quantum field theory, or QFT, and it's the most successful description of the universe humanity has ever built. It unites the strange rules of quantum mechanics with the continuous fabric of fields that fill reality. In classical physics, a field is something like a weather mapper, smooth distribution of values spread across space. For instance, a magnetic field has strength and direction everywhere. It can push on a compass needle or guide charged particles, but it's not a solid object. It's a pattern. Quantum field theory takes this concept and makes it fundamental. Instead of thinking of particles as little dots moving through empty space, QFT treats space itself as filled with invisible fields. Every type of particle has its own field: an electron field, a photon field, a quark field, a neutrino field. Wherever there's an electron, it's not a tiny billiard ball, it's a vibration, a localized bump in the electron field. When that vibration moves, interacts, or transfers energy, we perceive it as a particle flying around. The photon, the particle of light, is just an excitation in the electromagnetic field. So, in this picture, reality isn't made of things, but of ripples. The beauty of this idea lies in its consistency. The interactions we see, like an electron absorbing a photon, simply fields touching, exchanging energy, and returning to calm. When one field wiggles, another responds. Out of that mutual trembling arise all the forces of nature. Quantum field theory also redefined the meaning of the vacuum. In QFT, the vacuum isn't an empty background, but the lowest energy state of all fields. Even at that minimum, they never stay perfectly still. They oscillate, fluctuate, and interact with one another. This restless motion produces observable effects, from the Lamb shift in atoms to the Casimir force between plates. One of the triumphs of QFT is quantum electrodynamics, QED, the field theory of light and matter, developed by Richard Feynman, Julian Schwinger, and Sinatiro. It explains how electrons and photons interact with astonishing precision. The theory's predictions are so accurate that when scientists compare calculations to measurements, such as the magnetic moment of the electron, they agree to more than 10 decimal places. It's often called the most precisely tested theory in science. QED uses elegant tools like Feynman diagrams, those curious sketches of lines and loops that map the probabilities of particles interacting. Each line represents a field's vibration, and each intersection of vertex marks an exchange of energy. The diagrams aren't just illustrations. They're pieces of calculable algebra that have become the language of modern physics. Beyond QED, quantum field theory extends to the strong and weak nuclear forces. The strong force, which binds quarks into protons and neutrons, is described by quantum chromodynamics, QCD. Its name comes from the whimsical color charge that quarks carry: red, green, or blue, not colors we can see, but abstract labels that keep the equations balanced. QCD explains why quarks are never found alone. The more you try to separate them, the stronger the force becomes, as though space itself resists the division. This phenomenon is called confinement, and it's the reason protons and neutrons remain stable. The weak force, meanwhile, governs radioactive decay and the reactions that power the sun. It's carried by heavy particles called W and Z bosons, discovered in the 1980s. When combined with Q, the weak force forms part of the electroweak theory, a unified description showing that at high energies, these two forces merge into one. These three, the electromagnetic, weak, and strong interactions, form the backbone of the standard model of particle physics. It's our best description of how the fundamental particles behave and interact. The standard model includes a roster of familiar and exotic names: electrons, quarks, photons, neutrinos, gluons, and the Higgs boson. Each is a vibration in its respective field, and each follows the elegant mathematics of symmetry. The Higgs field, proposed in the 1960s and confirmed by the discovery of the Higgs boson in 2012, provides another layer of wonder. It pervades the universe, and as particles interact with it, they gain mass. Some interact strongly and become heavy, like the top quark. Others barely notice it, like the photon, which remains massless. Without the Higgs field, there would be no solid matter, no atoms, no stars-only massless light racing endlessly through a featureless void. So, in QFT, mass isn't an intrinsic property. It's a kind of resistance, a drag felt as particles move through the cosmic sea of the Higgs field. Quantum field theory is not just a model. It's the foundation beneath nearly every modern experiment in physics. From the behavior of electrons in semiconductors to the collisions inside the Large Hadron Collider, QFT explains it all. Yet, for all its success, it's incomplete. Gravity, the most familiar force, doesn't fit comfortably within it. General relativity describes gravity as the curvature of space-time, a smooth, continuous geometry. QFT, on the other hand, deals in discrete quanta and vibrating fields. Trying to merge the two leads to infinities and paradoxes. Physicists have spent decades searching for a unified framework, a quantum theory of gravity that would harmonize the large with the small. Ideas like string theory and loop quantum gravity attempt this, each proposing that space-time itself might be woven from microscopic loops or vibrating strings. If those theories are correct, then even space-time, the very stage of existence, isn't smooth, but granular. The fields we know may be melodies played on deeper, hidden instruments, but whether the ultimate truth lies in strings, loops, or something else entirely, quantum field theory remains our best working map of reality. It tells us that the world is not made of hard edges, but of music waves of energy playing through a cosmic field, harmonizing in ways our senses can only barely detect. And beneath the hum of that invisible symphony lies the quiet message that has echoed through all of quantum physics. The universe is not built from things, but from relationships, vibrations between fields, interactions between possibilities, the delicate balance of being and becoming. Gravity feels familiar. It's the pull that keeps your feet on the floor, the force that binds the planets to the sun, the quiet curve that shapes the paths of stars and galaxies. It seems simple, one of the first things we learn about the physical world. But when quantum mechanics arrived, it brought with it a puzzle that still hasn't been solved: how to make gravity and quantum physics agree. Einstein's general theory of relativity describes gravity not as a force, but as the curvature of space-time itself. Matter tells space how to bend, and space tells matter how to move. It's a breathtaking idea, graceful, geometric, and continuous. Quantum mechanics, meanwhile, describes a universe of probabilities, fluctuations, and discrete quanta. It works perfectly for the small electrons, photons, atoms. Yet the two theories, though both correct in their domains, speak very different languages. Relativity is smooth. Quantum mechanics is grainy. One deals with curves, the other with jumps. Bringing them together has been the central challenge of theoretical physics for nearly a century. If we try to quantize gravity to treat space-time itself as a quantum field, mathematics quickly collapses into infinities. The equations refuse to stay finite or renewable. It's as if nature resists being squeezed into a single description. Still, physicists have tried. One approach, called quantum gravity, aims to describe the gravitational field in the same way as other forces, as a field with its own quanta, hypothetical particles known as gravitons. These would be massless, traveling at the speed of light, and carrying the influence of gravity in tiny ripples through space, No one has ever detected a graviton, but if they exist, they would be unimaginably weak. Detecting one would require an experiment larger and more sensitive than any human construction could hope to achieve. Even so, the idea offers a bridger way to think of gravity in quantum terms. Another, more radical framework is string theory. Instead of treating particles as point-like dots, it proposes that everything is made of tiny, vibrating strings. Different vibration patterns correspond to different particles, and remarkably, the theory naturally includes a mode that behaves exactly like a graviton. In this picture, gravity isn't added on, it's built in. The geometry of space-time emerges from the harmonies of strings vibrating in higher dimensions beyond the familiar four. String theory is beautiful and mathematically rich, but it's also difficult to test. The scales at which its effects become visible are far beyond our current experimental reach. It may take centuries or entirely new tools to confirm whether it's the right path. There's another idea: loop quantum gravity. Instead of adding quantum rules to gravity, it tries to quantize space-time itself. In this view, space is not continuous, but woven from tiny loops, like a fabric of interlinked rings. The geometry of the universe arises from these loops, forming discrete chunks of volume and area at the smallest scales, the Planck length. About 1035, 1035, 1035. Meter spacetime would no longer be smooth. It would shimmer with quantum granularity, like pixels on an infinite screen. Loop quantum gravity predicts that black holes and the early universe might behave differently from what relativity alone suggests. Inside a black hole, for instance, the infinite singularity at the center might be replaced by a region of extreme but finite density abounds, perhaps leading to another universe beyond. This idea connects with another frontier, the study of black holes. These mysterious objects are perfect laboratories for testing gravity and quantum theory side by side. According to general relativity, nothing can escape a black hole, not even light. Yet, in the 1970s, Stephen Hawking combined quantum mechanics with relativity to show that black holes aren't completely black. They emit a faint glow, now known as Hawking radiation. It happens because of the quantum vacuum. Near the event horizon, pairs of virtual particles constantly appear and vanish. Occasionally, one particle falls in while the other escapes, becoming real radiation. To conserve energy, the black hole loses a tiny bit of mass. Over immense time scales, it could evaporate completely. Hawking's discovery revealed a profound link between quantum mechanics, gravity, and thermodynamics. Black holes have temperature, entropy, and even obey laws similar to those of heat. They are not cold voids, but dynamic systems encoded with information. This leads to another deep puzzle, the black hole information paradox. If a black hole evaporates away, what happens to the information about everything that fell inside? Quantum mechanics insists that information can never be destroyed, but Hawking radiation seems to carry none of it. Decades of debate have followed. Some physicists propose that information is somehow encoded in the radiation. Others suggest it's stored on the event horizon itself, in a two-dimensional layer, a concept known as the holographic principle. According to this principle, everything inside a region of space could be described by information inscribed on its boundary, much like a hologram storing a three-dimensional image on a flat surface. If true, this idea would revolutionize our understanding of reality. It suggests that our universe might be a vast holographic projection, three-dimensional, phenomena emerging from two-dimensional data at the edge of space-time. Though this sounds fantastical, the mathematics supporting it comes from serious research in string theory and black hole physics. It offers a possible bridge between quantum mechanics and gravity, uniting them in a shared geometric language. Whatever the final theory turns out to be, one thing seems certain: space-time is not as simple as it looks. It bends, ripples, vibrates, and perhaps even emerges from deeper quantum structures we have yet to glimpse. We live within this fabric, carried along its curves, shaped by its unseen threads. To us, gravity feels gentle and familiar, but beneath its calm lies a mystery vast enough to swallow stars. And somewhere in that mystery, between the smooth and the granular, the certain and the uncertain lies the key to a unified picture of reality, still waiting for us to find it. If we step back and look at everything quantum theory has taught us so far, one truth becomes clear. The universe is far stranger and more connected than our senses suggest. Yet, somehow, all this strangeness adds up to something stable, coherent, and beautiful. The microscopic world of uncertainty builds the macroscopic world of certainty we live in. Out of waves of probability come atoms, molecules, stars, and people. The bridge between those scales, though invisible, is constant and unbroken. In quantum physics, observation plays a powerful role. Not because the universe waits for human eyes to define it, but because measurement is the moment when possibilities resolve into outcomes. What we call reality is a tapestry of interactions, a web of relationships, where each act of measurement is a new thread woven into the whole. This leads to an idea both humbling and comforting. Perhaps reality isn't something that merely exists, but something that is continuously becoming. Some physicists go further, proposing that consciousness itself might play a role in how quantum events unfold. This isn't mysticism, it's an open question. When we measure, what exactly constitutes the act of observation? A machine, a human, a network of atoms interacting with light? The answer remains elusive. Others take a broader view. Consciousness doesn't collapse. Reality, it emerges from it. The brain, after all, is a quantum system, built from atoms whose behavior is governed by the same laws that rule electrons and photons. Thought and awareness may be the macroscopic echoes of microscopic probabilities, resolving in harmony, regardless of interpretation. The quantum world doesn't separate observer from observed. It reminds us that the two are deeply entwined. Every interaction is mutual. Every outcome a dialogue between system and environment. That same principle of connection scales up. Entanglement, the mysterious linking of particles across space, might not just be a quantum oddity, could be the foundation of everything we experience. Recent theoretical work suggests that the geometry of spacetime itself may arise from patterns of entanglement. In this view, space isn't a static arena in which events occurred, the result of quantum relationships knitting reality together. Distance and dimension emerge from how strongly things are entangled. It's a breathtaking thought that the fabric of the cosmos might be woven from threads of correlation, that here and there are just different patterns in the same universal web. Even time may not be as absolute as it seems. In relativity, time bends and stretches depending on motion and gravity. In quantum theory, time enters as a parameter in equations, but not always as something fundamental. Some physicists now wonder if time itself might be an emergent property born from change, entropy, and quantum interaction. Perhaps the universe doesn't flow through time at all. Perhaps time is the unfolding of relationships, one layer at a time, like the gentle turning of a cosmic page. As abstract as these ideas sound, they circle back to the same quiet truth we began with. Beneath all complexity lies simplicity, and beneath that simplicity lies mystery. The quantum world doesn't try to make sense in human terms, simply is. Yet, through careful observation and curiosity, we've learned to listen to its language, the hum of probability, the whisper of entanglement, the rhythm of uncertainty, from Planck's first quantized packets of light to Einstein's reluctant photons, to the wave-like electrons of Schrödinger and the entangled ghosts that so troubled Einstein. Each discovery has led us deeper into wonder, and still, every answer raises another question. Why does measurement collapse the wave? Why is the speed of light the same for all observers? Why does the universe prefer symmetry but occasionally break it? We may never know all the answers, but the search itself is part of what makes us human. Our minds are tuned for exploration, for building bridges between what we can see and what we can only imagine. Quantum physics reminds us that certainty is rare, but beauty thrives in uncertainty. It tells us that the world is built not from rigid laws alone, but from probabilities, potentials, and relationships. In that sense, it's a profoundly hopeful theory. It suggests that reality is flexible, that change is built into the fabric of existence, and that possibilities are never entirely lost, only waiting to be observed. So, as we drift toward sleep, let these ideas settle gently. Picture the universe as a vast sea of waves, each one tiny, fragile, and uncertain, yet together forming the grand harmony of everything that is. The stars above you, the atoms within you, the space between, all part of the same cosmic music. Vibrating softly through the stillness of time, close your eyes and listen. The universe hums quietly, and you are part of its song. And so, our long and gentle journey through the quantum universe comes to rest. What began as a mystery of glowing metal and strange equations has unfolded into a portrait of existence that is at once mathematical and poetic. It started with Max Planck, sitting in quiet frustration, searching for a way to explain why hot objects glow the way they do. His simple fixer, constant so tiny it almost seemed trivial, opened the door to everything that followed. Then came Einstein, turning light into particles, proving that energy arrives in indivisible quanta. He didn't just solve the photoelectric puzzle. He revealed that the universe itself comes in discrete notes, as though reality were written on a cosmic scale. Schrödinger and Heisenberg gave that scale its rhythm, the wave equation that let matter sing, and the uncertainty principle that set its limits. Together, they showed that knowledge and reality are never fully separate. We can never pin the world down completely. We can only trace the patterns it allows us to see. From there, the quantum story expanded outwards: entanglement, tunneling, the restless vacuum, and the invisible fields that ripple beneath all matter. Each idea stranger than the last, and yet every one tested, measured, confirmed. The strange became the ordinary. The impossible became the basis of our technology, our stars, our lives. Quantum mechanics gave us lasers, transistors, computers, and the glow of every modern screen. It taught us how the sun burns, how atoms bond, how time and space may rise from deeper patterns of information. It even suggested that the universe might be holographic, every part containing reflections of the whole. And still, after more than a century of discovery, it remains incomplete. We know the laws that rule the small and the laws that rule the large, but the bridge between them still eludes us. Somewhere between gravity's smooth curves and quantum theory's grainy dance lies a hidden unity waiting to be found. That mystery is not a failure. It is an invitation. The unknown keeps the universe alive. It gives science its pulse and the mind its wonder. We are not separate from it. We are made of it. Every atom in your body was once entangled in the hearts of stars, once part of the same universal wave. When you breathe, you exchange particles that have drifted through galaxies. When you think, you rearrange tiny quanta of energy that were born at the dawn of time. You are, in the most literal sense, a piece of the cosmos becoming aware of itself. Perhaps that is what quantum physics has been whispering all along, not just that the world is uncertain, but that everything is connected, that we are woven into the same fabric of probabilities, entanglements, and fields that shape the stars, even in its deepest equations. Quantum theory carries a quiet kindness. It tells us that possibility never ends. Out of uncertainty, life finds form. Out of probability, the universe finds beauty. So as the night deepens and the world grows still, imagine all those invisible waves continuing their dance, the electrons swirling, the photons gliding, the quantum foam shimmering in the dark. You are part of that dance. You always have been. Rest now within it. The universe hums softly, folding its endless questions into the calm of sleep.